It's really, the talk is mostly about a project we've been working on, but I also want to mention some of the ideas which we've had problems with, which we think the project will lead on to, which is where the data staging aspects really come in. The project's a Framework 7 FET project called NextMuse, Next Generation Multi-Mechanics Simulation Environment. I was very impressed by the EU because they said because it's an FET project, failure is an option, which I want you to bear that in mind throughout the rest of the presentation. The partners we're working with are doing particle simulations. They're interested in ships. They're actually branching out to do things like wheels and doing a conventional modeling of CFD on these kind of treads and things is quite expensive, but with particle methods, because you only have to represent the boundaries, it makes the job much more tractable. In particular, ships, they're interested in, the ship is sloshing, and if there's a tanker of oil or something on top of the ship, and that's sloshing in its own frame of reference, and the ship is then being disturbed by waves, how do these couple, how do they interact? And if you move things around, how does that change? And what they'd really like to do is they'd like to use the computing resources as an interactive tool, so they can have the ship and push it left and right and see the graphs change and then change something and read, and they don't want to run things as batch jobs. They want to actually work like engineers where they're testing a harness, they're running in real time. Another project, another partner I should say, is working on heart valve design, and they're really interested in if you model the blood flowing through the valve, are the red blood cells basically ripped apart by the stresses as they pass through? And if you change the shape of the valves, and if you add a chamfer here, if you move them there, how does that change? And could we have a knob that you can pull which adjusts these kind of things and they can see the stress being plotted on screen, that kind of stuff. And from our point of view, the most interesting one is these Pelton turbine people. We've actually worked with these people in a lot of projects over the years. And they, I'm hoping this, there should be an animation, but I guess, oh, that's a shame. I wonder if it plays if I do anything on here. Okay, well, what you should see is the bucket turning round. Over here you have jets. Water comes down, there's a lake on the top of the mountain, the water comes down a pipe, it comes out of this jet here, hits this bucket, and then it splashes out. Now the buckets all spin round, and the shape of this jet actually plays quite an important part in the momentum transfer, the energy transfer into these buckets. And these wheels are actually usually mounted in a horizontal frame of reference, so they spin like this rather than like a wheel. And what happens is the water splashes out, and this casing is all basically sealed. And when the water splashes out, if they can have as many as 6 jets all around here, and if the water comes out there, splashes, and then lands on another jet, it disturbs the flow, which in turn causes the jets to spray out, which you lose momentum. And even if you only lose a fraction of a percentage of the energy, it's actually megawatts that they're talking about over a period of months and years. And so what happens is the water comes splashing out, and it comes all over in this region, and what they want to do is put little plates in to just deflect the flow. And they'd like to be able to just move these plates around and see how the flow changes as they're doing this. So what they really want to do is play with the designs. Instead of running a batch job, seeing the results, plotting them out, then submitting another one, they want to just play with the stuff, which is where the project really is going. So we have requirements. We want to in-situ visualize their simulations, but we want to actually do computational steering. We want to potentially take all the particles on the mesh, move them a bit to the left, and then send them back into the simulation to change something fundamental. We don't just want to send a parameter alpha, change it from 0.2 to 0.3, which is some velocity factor. We actually want to be able to change a whole surface, move it around, because they only deal with the surface meshes, and you don't have this complex FEM model where you have all the, the interacting tetrahedra. It's actually much more tractable to do. We can consider doing it. So potentially, I beg pardon, wrong button, large data, two-way. And some of them are Fortran, some of them are C, some of them are C++. We've got different codes to work with. And they really, as I said a moment, they really want to treat their cluster or their supercomputer just like it's the workstation. They don't want to have to worry too much about all these things that we deal with every day, but they don't know much about. The constraints being the partners, they're all located around the world. And they're really physicists, and they don't know an awful lot about really good programming techniques. So they want to have as simple as API as possible. They want to just say, just give us something that works, let us play with it. When it breaks, we'll ask for help, that kind of thing. In the ideal world, you'd run your simulation on a whole bunch of cores, you'd link all the visualization and analysis code directly to it, everything would just be coupled together as one huge great MPI job, and it would all work very nicely. And Visit and PowerView used this for in-situ visualization. This scared us at the start of the project because some of the visualization stuff just doesn't scale as well as the simulation might do. And if you do this, you may effectively destroy the simulation by putting bad analysis into it, effectively. And so what we really wanted was, rather than breaking the simulation, is to have a more loose coupling where, if you're familiar with parallel file systems, the simulation writes out to OSS nodes. This is a Lustre example. GPFS is basically the same, which then gets sent off to disk. And we said to ourselves, well, if we were to just replace those OSS nodes with distributed memory nodes, DSM there, which is our data staging area, instead of writing to disk, we could just write to some memory area, which the simulation and the analysis can connect to. And in this case, we have the viz nodes over here, which are connected to the DSM. In fact, this green box means that these DSM nodes and these viz nodes are actually the same. Or alternatively, you could have the simulation hosting these memory nodes and you could have them the same. So it's sort of flexible in the sense that you could have the simulation allocate a memory buffer and everything works from that. Or you can have the analysis allocate a memory buffer and everything works for that. And they're both distributed and you can kind of choose which you want. And this is what we refer to as a loose coupling model because we haven't physically linked the two applications directly together. We're coupling them using an MPI type of approach. And in fact, we use a com publish, com accept, so you can dynamically connect. And some of the advantages of a loose coupling are that you can have, for example, a simulation machine up here connected via either an InfiniBand switch or if it's on a some other network, to an analysis machine. And then because we're using a PowerView client-server framework, we can have the GUI running on your workstation, we can have a Viz cluster doing this, and we can have the big Cray doing that. Or we actually find that this is the one we use all the time. We have the Cray, for example, doing simulation and analysis, or the Viz cluster doing simulation and analysis, and the workstation on the desktop. And you could even have all of this going on just on the desktop and this. In fact, you could do the whole thing on just one machine if you want to, but I didn't bother including that. It's kind of flexible, and as long as you've got a network connection between them, you can do it whichever way you like. When you actually use our implementation, where I think I probably skipped a couple, actually. I cut some slides out from my original presentations. HDF is where we came from on this, is that we told all our project partners years ago, before this project even started, we were working with them on other things, and we said, look, use HDF, it's great, because you can write out in parallel, the files are easy to use. And this is what kind of led us into this world. Now, it turns out that HDF has a rather simple interface which allows you to basically strip out the file driver layer and replace it with your own driver layer. So that normally when you use HDF, you say, create a file, and you create a property list, which is how you access the file. And when you're using Parallel, you use an MPIO. So you say, give me the MPIO-based file driver, and then you write out, and it all goes through MPIO. To use our stuff, all you have to do is literally replace the file driver with what we've called our I'm looking at the wrong line. You insert a DSM file driver instead of an MPIO driver. It's basically one line of code changes, and then instead of all your data going to the disk, it goes into our memory buffer. And from that point of view, it satisfied our main requirement at the beginning, which is we've got these Fortran people, these C people, they're physicists, they don't really think, well, a simple API. They really only have to make one line of code change, and all their data just goes into our buffer instead of the disk. We've completely bypassed all the MPIO, all the Lustre striping, all of that stuff. Just forget about it. And then you just carry on. You create a data set, you write into it, you create your normal property transfer lists. I won't go into the details there. And the file driver itself is, you have nodes where you've allocated memory. In this graph picture, we've got 4. And you open the file, you write stuff into it, you close the file, and then the analysis can open the file and it can query it. Now, the more nodes you use, the more links on the network you're likely to be using. In this case, we've got 4, and if it's on the Viz cluster, it's 4 links. If it's on the Cray, then it's 4 times by 3 dimensions, because they've all got links to different things. And how you actually send data into these depends on which machine you're using. And we have layers, basically a communication layer, which is like a plugin. It's a C++ class, and you can create your own ones. And we have a TCP, MPI, a one-sided MPI, and a DMAP, which is the distributed memory application one, which runs on the Cray really close to the hardware. And something I should point out, the more links that you're using, the more bandwidth you're likely to get when you write data into it. Now, when you create an HDF file, and this applies to any file, but we'll just talk about HDF here, it's basically you allocate a bunch of space, and then you write data into the space. And if you allocate, let's say, a 1 gigabyte memory buffer, and then you write 1 gigabyte of memory into it, then everything's lovely, because what you're effectively doing is you're sending all of these parallel tasks up here. Let's suppose your simulation's running on 512 or 1024 processes. It's all being written through different links into these 4, and because your memory is, because you're filling the memory, you're using all the links in the network. And so, I should point out there's metadata here, which is the sort of how HDF manages what's in the data in the file. When you write into it, you fill up the memory, you use all the links, everybody's happy. But actually, most people don't do that, because you open the data, you open up the file, and you write lots of small data sets into it, usually, rather than one enormous one. Now, if you do use the whole file, on, for example, the InfiniBand cluster, we get, can anybody read these numbers? I'm suspecting no. They looked better on the screen, but they look a bit too small up there. On a small cluster, if we have 4 nodes holding a, 4 nodes each with 4 processes, allocating a DSM, we write into it, and this, I think, says 10 gigabytes per second. So you open up the file, you write into it, you close it, and you get about 10 gigabytes per second because you've basically used all the links. On the Cray, we're getting about, gosh, I can't read these numbers at all. It's about 40, 50, peaking up somewhere around 60 gigabytes per second, using 160 processes, 40 nodes. So we've effectively got 40 links, or 40 Gemini sockets effectively active. And so we're getting pretty good bandwidth in the sense that we've got a whole bunch of, I forget now how many, is that 2048 over there? I can't see the numbers. 2048, I think it is. Host process, the simulation's running on 2048, and it writes into that, and it basically uses all the links that are available, and you get a very good bandwidth. The problem is that you normally don't do that. You actually write out one array, like pressure, then temperature, then velocity, and you've, in a sense, you've serialized your I/O, because what you do is you go dataset create, write it out, close that dataset create, write it out, close that dataset. You've kind of serialized things, and what happens is then is all of the pressure is going to this memory area here. All of the temperature is going to this. All of the velocity is going to here. And you're only now using a subset of the links. So you're not going to get the bandwidth you thought you were getting initially. And a very simple solution to this is to just not have a linear address mapping here. This flat linear address space. Unfortunately, HDF only gives us a linear address space. But there's a way around it, which is that we can, skip the animation, you can guess what's happening, is to, instead of mapping the HDF memory to our DSM memory, we can insert a layer in between, which is like a virtual address layer, and we can add in like block cyclic or random block allocation, so that instead, when you write the pressure array, it's split a piece here, piece here, piece here, piece here, the next piece here, next piece here, next piece, and then the temperature. Now what we've done is we've split the data, fanned it out, so that we're now using many, many more links. And when we do that, we find, these are some micro benchmarks, I'll come back to those in a second. When we do that, we find that if we write out just a linear memory, but we write lots of small data sets, we get a comparatively low, this is a two-sided MPI, and that's a one-sided MPI, and that's I beg your pardon, this is a DMAP. This is the DMAP communicator, the green one. You find now the same conditions, we're getting 60, 70 gigabytes per second into our DSM, even when we're writing out lots and lots of small data sets. In this example, we're writing out 10. And in fact, these graphs here are actually the result of doing lots of little micro benchmarks where you say, well, let's have a block of 1 kilobyte, 2 kilobytes, 4 kilobytes, run lots of tests, and you generate all series of graphs and think, okay, the best one turns out to be. And you see exactly the same little drop points that Professor Panda showed us earlier, where you switch from the small, the direct memory copies to the buffered memory copies inside the MPI layer and also inside the Gemini layer. Oh, I'm going the wrong way, I'm sorry. So the bandwidth is really nice, and bear in mind that here we're using basically 40 gig DSM on 160 processes. If we doubled it to 320 processes or 500 processes, then we expect the bandwidth to scale pretty much linearly because we're just saturating the network with these little blocks of data going out. In principle, if we took the machine and we said half the nodes to be senders and half to receivers, we think we'd get pretty close to the bisection bandwidth of the machine. But actually placing the nodes in exactly the right way so that you were modeling exactly along one X, Y, or Z plane, we haven't actually done it. It's worth comparing that other people are doing very similar things, and there's a package out there called Data Spaces, which is being developed by Rutgers and Oak Ridge. And theirs is different in many ways, but the basic concept is the same in that you have memory, which lots of people connect to. They write stuff in and they read stuff out. By using HDF, what we've actually done is we've kind of circumvented. We've said, HDF, here's a data set. When you write it into the file, HDF does all the generation of the memory addresses for us, in the sense that what they effectively do is they use hashing functions, say, here's an array, which is n dimensions, or here's a space-filling curve, which you can map to one dimension, and this piece of the array is going to be sent into this region of data, this region of the file, and there's a quite complicated layer of logic in there which maps pieces so that if 1,000 processes are writing chunks in, each gets allocated different bits of memory and they write it to there and write it to there. HDF basically does all that for us. It is a file system in its own right. It manages all the addresses. The only downside is that we can only use this linear address space. And of course, we only support 2 connections at the moment, and not completely simultaneously. The graphs I showed you a moment ago are basically benchmarks. One of the solvers we're connecting to is called SPH flow. And one of the examples that we use is a wedge which is dropped into the fluid and it sort of sloshes around. When we connected this up to the DSM, we found that if we measure the disk I/O, scaling it from 1 to 1,000 processes, and we just integrate the total time it uses to write to the disk, we find that it comes out like that. If we replace it with the DSM, it looks more like that. This is a log scale. So it's almost 2 orders of magnitude better. So down here, we're getting 200 gigabytes per second, and they're getting 2 gigabytes, roughly. And as a comparison, the total CPU time that they're actually using, I should say that this is a reasonably weakly scaled example, because the code only runs effectively if you have a minimum of about 50,000 particles per core. So when you're running on 1, you're doing 50,000. When you're running on 1,000, you're doing 50 million or whatever the numbers work out as. So what you're writing out is, you're writing out 200 gigabytes here. You're only writing out 200 megabytes here, effectively. But what's happening here is, everybody knows, I mean, half the people in the room seem to work with I/O companies, is that basically the disk I/O isn't scaling here. And actually, this is not a very fair test because you wouldn't write the stuff out every single time step. But actually, with our DSM, you basically can, because it's all just memory-to-memory copies. And the turbine people, for example, how does it look when we use it? Well, essentially, we've bolted everything into a PowerView interface. You start the simulation. In fact, we've made it so that when you connect up here, you can basically click a button, you can submit a Slurm job onto the thing, it launches the solver, it launches the DSM host, they connect, everything connects back to the PowerView, boom, and you instantly get it. The interesting thing is that visualization is very, very easy, because they write into an HDF file, and you just read it out. You don't have to do anything. You only make one line of code change to the solver to say, use our DSM. Visualization is very, very simple, as long as you know where to find things in the file. And actually, HDF is supposed to be self-describing in the sense that it tells you what's in its file. I find it a somewhat strange way of describing it, because HDF is the most horribly complex file thing. You can store anything in any combination. You can have pressure arrays, temperature arrays, geometry arrays, topology arrays. They can be all randomly placed. So what we do is we make the, oops, I beg pardon, we make the guys write a little template file, which basically says in the HDF file, there's a fluid group, and in that there's position, there's density, there's velocity. As long as we know where those are, then we can read those arrays out, we can map them to geometry, and we can display them on the screen, everything's happy. It's not so easy when you want to do computational steering because we can, I made a deliberate spelling mistake up there, just in case you're worried. When you do steering, you want to write things back into I should point out that because this buffer it's two-way. They write into it, we read from it, but we can write into it and then we can tell them to read from it. When you do steering, things aren't the same because I can't suddenly magically make someone's solver do things it couldn't do before just by sending data to it. I can crash it very easily. In fact, we were experts at that. We can send all sorts of rubbish into the solver and bring it down very easily. So steering is much harder. And the other problem with the steering is that we've got turbine people, ship people, heart valve people, and they all want to see something different. One guy wants to change the shape of the heart valve, one guy wants to push the ship left and right, one guy wants to change the shape of a bucket or move a jet around. And they don't want to write any code themselves either. So we've leveraged ParaView again, which has a rather nifty facility, which is when you write a filter in ParaView, it says, I want to take all this, I want to do something to it, and then you have 3 parameters. You can specify a little bit of XML, and ParaView parses that and generates little GUI controls. And we've extended that very slightly to allow us to create steering controls where the engineers write some XML, which basically says, you're allowed to modify this, you're allowed to modify this, you're allowed to modify this. This is a 3-component XYZ vector. This one is just a simple scalar. And we also allow you to write meshes into us with this name and in this location and with this certain criteria. We pass all that XML and we create a GUI for them so they can then control their simulation basically without having to modify any of our code. They can modify theirs all they want because one of the problems we have is if you say stop the simulation, reload a new mesh, continue from where you were a minute ago and carry on, it invariably doesn't work because they have to modify their code there's all sorts of reinitializing boundary conditions, all sorts of other things that go on. They have to do that in their code, but they can add arbitrary buttons and you name it, which, for example, this one here, restart the simulation or reload the mesh. The GUI doesn't have any idea what those buttons do. All it knows is it was told to put a button on the screen, and when it clicks it, it sends a particular command into the DSM, and effectively it writes a data set with a little flag saying, do this. Simulation picks it up and it can do what it wants. So it's quite clever. It's a bit like a compiler compiling itself. The engineers can put anything they like in it. It appears in the GUI, and when you click it, they can then make the simulation do whatever they want. And so they don't need any specific knowledge about how our stuff works. Of course, if they wanted a specific custom control to control heart valves, they would have to do some special work to make that happen. But if they just want standard controls, then everything's fine. When we do the steering, there's really 2 ways things can go, which is that the simulation can run, and it can write stuff out, and then it can say, okay, I'm waiting for some response from you, so it sort of waits. And then the GUI, you play with stuff, and you change things, and you say, okay, I'm happy with that, and then you say, carry on, and the simulation carries on. And we call that wait mode. Or you can have the simulation just running and running and running and running, and every now and again from the GUI you think, oh, that doesn't look right, I'll just change that and send it. And then the next time the simulation picks up a change, it does what it wants. In this case, you have to always be aware, the simulation has to be aware that it's working on time step t+1 whilst you're still analyzing time step t, so there's always going to be a slight problem there. A nice example is the turbine guys, they said, well, the bucket is being eroded. If we put more sand in the jet of water, the bucket is getting eroded. If we could have the erosion very slowly making the bucket get thinner and thinner and changing shape slightly so we could see the difference, they don't actually need every single iteration to receive a new bucket. But every 20 or 50 or 100 iterations or every certain number of wall times, they could take that and put a new, just remesh the bucket, send it back with a slightly thinner surface. change the pressures on various parts of it. And when we actually run it, it looks a bit like this. This is quite a small example. Unfortunately, the engineers haven't quite scaled their code to the point where we can really do a full ship and send it back and change things. But we can do some small, simple ones. And in this case, we have a simulation which is running on, I think, 12 or 24 cores. ParaView is running on 4 cores. And we can receive data, we can resample it to a grid, we can isosurface it, we can take meshes like this sphere, for example, generate them in parallel, write them in, because the important thing is that we're writing into the DSM and we're writing in parallel, they're reading in parallel, they're writing, everything's going on in parallel, it's a proper parallel file system. And all of this sort of GUI stuff over here is generated. We found it's actually remarkably difficult. I'm hoping the next animation works. Okay. I think here's an example, is that they don't normally model bunnies being dropped into their fluid. But as an example, and this is a special Benny Hill version because I've speeded it up slightly, because if you sit and watch somebody doing this, it's pretty tedious. But basically, we found it's very difficult to take an object whilst they're running the simulation and move it around, because we forgot when we wrote the proposal that their simulation is running in microseconds. Each time step is 10 to the minus 6 of a second. And you're sitting there with a GUI moving things around in your real time. It's absolute nonsense. So we couldn't really do anything useful. Then we realized that within ParaView, there's an animation where you can set up keyframes, and the time is somewhat abstract. So we can say, okay, look, take that bunny, squash it, stretch it, shrink it, do things according to a certain keyframe animation, put them all in there, then hit the play button, and then off you go. And so we can effectively, over here, actually, I got a bit ahead of myself, but over here there was a wedge. What we've done is we basically said, stop the animation, reload this new mesh, and then we can connect a pipeline in ParaView. So we can say, take the mesh, that was nasty. We can say, take the output of the simulation, apply this filter to it, apply that filter to it, resample that, apply that to this. Now take the output of that and send it back to the input, which in their case, there's a special control over here which represents an input back to the simulation. And in our case, we're taking the output of the transformed bunny, sending it back into the simulation, so that on each time step, it automatically gets a new mesh, and it says, oh, new mesh, and it reloads that, reinitializes the boundaries, and then carries on the simulation. So effectively, what we're doing is something very similar to adding deflectors into the turbines, although in this case, it's just a bunny. And what we're trying to demonstrate with this little animation is that we've paused the simulation. We think, okay, we want the bunny to do that, want the bunny to do that. We click, okay, when we're ready, then we set everything up. There's a button over here somewhere which says wait. And when we say don't wait anymore, because the nice thing about the way the XML is done is that you can add a command, wait. And when somebody clicks this, stop waiting. So you can, the simulation can say to itself, all right, every 100 time steps, I'll check, and then maybe go back into a wait mode, unless they've told me not to, and then I'll go back into free running mode again. So you can kind of flip between modes. Anyway, so then the simulation carries on, bunny goes off, and this all really works quite well. We just need a full ship and a big engineering test case to try it on. Here's another example which probably won't play, but never mind, doesn't matter. That was just a wedge being pushed through the fluid. When we created all of this, we kind of realized that it works quite well and it's quite good, but there's some things that are really wrong. And the main one is the memory. From my point of view, the main one is the memory. The simulation generates a pressure array, and it might be gigabytes. If we scale this up to run on really big machines, they might write a really big array. They write that into the DSM, so there's another copy there. And then we read that out into our ParaView, and we've got another copy there. We may have 3 copies of the same data, which it's just, I mean, we couldn't get round it. We have this linear address space. Now, all of you are compute nodes, and you've all got one piece of pressure. And I'm a whole bunch of analysis nodes, and I all want the piece of pressure, but I also want the same piece of temperature. I don't want the temperature from over there. I want the temperature from there, and I want the pressure from there, and I want the velocity from there, and I want that all on my piece. And this node wants the pressure, and so you want the pieces, these little blocks of data that are being sent around to all come from the same pieces of the grid to the same analysis nodes, and you don't want it to all just spread around. The way that's handled at the moment is the DSM. You write in, I read out. I have my own hyperslabs, you have your own hyperslabs, everybody's happy, but there's this extra copy. If we start sharing memory, then we have to be much more clever about the pieces as well. And so array sharing, we want to be able to have multiple clients. So various people can connect to it and do different things. I might be interested in pressure, you might not be interested in pressure. We don't want to copy pressure too many times if somebody's not using it. Case in point, what we'd like to be able to do is instead of creating pressure, velocity, density, mapping them into DSM and then reading them into arrays in VTK, we'd like to just allocate them once and write them directly in. And the HDF guys have proposed what they call a virtual object layer. The real problem we've got is that when we open a data set and write data into it, all we see is memory addresses. We don't know that that write of 1 megabyte, which came from that node, is the pressure array from that piece of the grid. We don't know, all we know is that we got 1 megabyte that we do a put and we do a get. We have no knowledge about what's going on above us. If they implement a virtual object layer, then when you create the data set, you'll actually be able to create this array dynamically. So instead of having a fixed DSM, which just sits there, and you just write stuff into it until it's full, you'll say, I want a pressure array, and you'll allocate a piece of memory, and that'll be the pressure array. And if you're allocating the memory yourself, you can use shmem or something like that, and you can actually distribute that and stripe it so that the pieces are actually mapped onto the nodes you want and write it straight to them. Bypass a lot of stuff in the meantime, excuse me, which harks to this distributed, what was it? Distributed application objects we saw yesterday in the Luster talk. This is exactly what we want. We want distributed objects which are referenced. But we'd like to go a bit further than that, really, because we want those pieces, as I say, so that the pieces of pressure, the pieces of velocity, and the pieces of density from each bits of the grid to all go to the same nodes that are doing the analysis. And we can do that to a certain extent because we have this block mapping, we have the virtual address lookups. So we can kind of do that already, except that we don't know which piece each one belongs to. And if, for example, you're running simulation cores, analysis cores, which are actually on the same node, and they've actually got the same memory, what you really like is your memory manager to know that this block that's being generated by the simulation and is about to be analyzed by there, if that analysis node is somewhere else, to copy it, but if that analysis node is actually, or rather, ignore that for a moment, if this piece of data is actually running on the same node, to leave it where it is and not copy it. And sometimes you might say, well, it's too expensive to copy that memory, couldn't we just do that analysis on that node? Then the problem comes in is this whole framework, which relies on streaming. It's like a sausage factory, which is what these are supposed to be. And this is not happy when things are moving around, because we work with fixed pipelines where you do this, you do this, you do this, you have a workflow. When you start having dynamic people connecting, I want this filter, this filter, this filter, and then I want to delete that and I want to add this, everything starts getting much more complicated. So what we're really looking for is a much more sophisticated memory manager which turns the simulation into an interactive instrument so that people connect, and the people who want the memory can access it, but if you don't want the memory, it just gets dropped. So everything's reference counted, everything's shared, and things are copied on demand or dropped on demand. And if you were to take all of that DSE and stuff it into the DSM and stuff it into a huge rack of SSDs and have a disk where you have persistence, because we see people saying, right, stop the simulation, go back 3 iterations, resume it from there, but remember those results, you just stuff them temporarily. I don't want to put them to disk, but I want you to just store them there for 5 minutes whilst I rerun that bit. Now I want to compare those two. I want to compare the other results. We need to be able to access potentially thousands and thousands of different pieces of arrays and have them all accessible so that we can compare and contrast, so that one guy can look at these, one guy can look at these, and all those arrays are somehow intelligently mapped. That's what file systems do very well. And what we really want is a memory-mapped file system, except we don't really want files, we just want objects, which I think that DAOS summed up very nicely. This is my final slide. Just about on time as well, lovely. We haven't done this, but this is where we're going. Any questions? I'm out of breath now.